In this talk, I'd like to talk about an application of tensor network to quantum computation. It's not a simulation algorithm, but we have described a quantum circuit by tensor network language, and we have investigated the computational complexity of this quantum circuit. Specifically, we have considered dual-unitary quantum circuit, which have been recently studied as exactly solvable model of quantum chaos or summarization dynamics. And dual-unitary is written by tensor network language. And briefly speaking, the result is we found that dual-unitary quantum circuit makes computational complexity phase transition. That in early time they are they can perform very easy computation, but in later time they can perform universal computation. That we consider that the problem is they can solve very hard problem. And this is joint work with Kosuke Mitai-san and Keisuke Fuji-san. They are a faculty in Osaka University, and I mostly conducted this work when I was in Osaka University. Yeah, and this is based on this paper. Okay, let me start this talk. So first, my talk is about quantum computation. So I'd like to briefly introduce quantum computation for those who are not familiar with it. Quantum computer is a computer which makes use of quantumness, such as superposition of quantum state. So that makes use of superposition, or more sophistically, it's called magic lens, and so on. And what do we do? We prepare quantum state first as initial state, and we apply quantum operation such as unitary operation or measurement many times. And finally, we read measurement outcome by observing local observables, and we regard these output as computational output. And it's known that this quantum computer can outperform classical computers for certain problems, such as factoring problem. So factoring problem is given an integral and decide whether integral m divides integral n or not. And it's known that this factoring problem is solved by quantum computer efficiently, but there is no currently classical algorithm to solve factoring problem efficiently. And there are several quantum computational models which are equivalent to each other. So I want to briefly explain. So first one is circuit model, where we prepare quantum state and we apply unitary gate or unity operator on single qubit or 2 qubit sequentially. And another computational model is so-called measurement-based quantum computation, BQC, where we prepare entangled state first and measure this state adaptively. And another interesting example is so-called adiabatic quantum computation, where we change Hamiltonian adiabatically and compute by computation is performed by ground state of Hamiltonian. And in this talk, as I said before, I will focus on circuit model. So I'd like to explain more about circuit model. So the quantum state is described by qubit, and we apply unitary operator in this. So we write a unitary operator like this, and we apply unitary operator sequentially. And output depends on the problem that we want to solve. So we measure local observables when we want to solve decision problem, such as, or yes or no problem, such as factoring problem. And there are another problems, so-called sampling problem. So the problem is to sample from this wave function of final output state. So final output state is highly entangled state in general, and the sampling problem is to sample some single product state from the final entangled state. And this problem is used for showing quantum supremacy, and recently Google asserted to achieve this quantum supremacy. And it's known that we can generate arbitrary quantum circuit by using only this 3-qubit gate, only these 3 unitary gate. So first one is Admar gate. This is a single qubit gate written like this form. And second one is T gate, which is also a single qubit gate written like this form. And last one is CZ gate, which is 2-qubit gate and makes entanglement between 2-qubit gate. And this is written in this form in matrix. And they can approximate arbitrary unitary operators, which means that we can replace this unitary operator by these 3 operators. And interestingly, a CZ gate can be replaced by arbitrary entangling 2-qubit gate. So there is very natural problem, question about quantum computation. So as I said before, quantum computer can solve a hard problem for classical computer. So the natural problem question is what makes quantum computation different from classical computers? So accordingly, when is quantum computation tractable for classical one is also important problem. What I mean is, in general, quantum circuit, to simulate quantum circuit is hard problem for classical computers, so they cannot simulate efficiently in general. Otherwise, they can classical computer solve a factoring problem or something like that. However, if we make a restriction on unitary gate, then sometimes we can simulate this quantum circuit efficiently, which is so-called classically simulable quantum circuit. And a famous example of classically simulable quantum circuit is so-called Clifford circuit, introduced by Gottesman. And the Clifford circuit is a quantum circuit composed by these 3 qubit gate, Admar gate, T gate squared, CZ gate. So we replace T gate in universal gate set by T squared. And they have a very nice interpretation in conjugation of Pauli operators. So when Clifford gate conjugate a Pauli operator, then the outcome is also Pauli operators. And because of this structure, Clifford circuit composed by these 3 unitary gates are classically simulable. Because quantum computer can track these Pauli operators. Another famous example for classically simulable quantum circuit is called match gate. And match gate consists of 2-qubit gate written by this form. So here A and B is unitary operators in SU2. And they are not only interesting for fundamentally, they have, but also they have application on about, for example, about error estimation of quantum operators, which is very important for realization of quantum computers. And this classical simulation is also useful for evaluating performance of quantum error correcting code, which is also very important um, for trend quantum computation. It will be required to perform universal quantum algorithm. And what's more interesting for us, this classical experimentable quantum circuit is related to exact superball model. So it is very natural because they they are simulated efficiently by classical computer. So it means that the calculation of something is easy for easy for classical computer or human. So it's natural to expect that it's related to exactly solvable model for non-equilibrium physics. So I want to talk briefly about how non-equilibrium systems are related to quantum computation. So recently, isolated quantum systems has attracted growing concerns due to mainly the development of quantum techniques or experimental techniques such as control of cold atoms. And one interesting research field is to study how quantum isolated systems equilibrate to thermal equilibration, so-called thermalization. And another interesting phenomenon is quantum chaos, and the definition of quantum chaos is a very controversial and a hot topic. And to explain this phenomenon, we develop exactly solvable model, and the well-known example is free fermion model, although they do not thermalize and are not chaotic. And interestingly, for quantum computational community, free fermion is exactly equivalent to a match gate as I defined before. And although match gate is introduced by computer science variant, and it's independent interest of physics, but after that, the relationship between free fermion and match gate have been discovered by Tahar and Levin-Venson. And recently, dual-unitary quantum circuit, which is exactly the model of thermalization and quantum chaos, has been discovered. And in this talk, I want to find a classical symmetrical quantum circuit that is a counterpart of dual-unitary quantum circuit. So I want to say the definition of dual-unitary quantum circuit specifically in one-dimensional model. Dual-unitary quantum circuit is quantum circuit where the initial state is certain initial state I will define later slide, and the quantum circuit have a brick wall structure. Here I write lateral side as space and this side of time. And the dual-unitary gate, each of gate dual-unitary gate, and the gate is defined by following. So we write unitary as a tensor network language, and the origin after reshuffling indices, I mean the original unitary, we take I and j as input and k and l are output. But if we shuffle indices, I mean we regard I and k as input and l and j as output. Then if this U bar is also unitary, graphically it's written like this, then we call that original unitary is dual-unitary gate. So because of unitarity, they satisfy this unitarity condition. But if they satisfy also this unitarity condition in space direction, we call this as a dual unitary gate. And the example is swap gate. So yeah, it's trivial if we see graphically. So in this time direction, this is swap gate, and also in space direction, this is also swap gate. So swap gate is dual unitary gate. And oh, excuse me. And counter example is identity gate. So if we see identity gate from the lateral view, this is the projector, not unitary. So identity is counter example. And it general form of dual unitary gate are known. So they can be written like this. So now U1, U2, V1, V2 are arbitrary single qubit gate, and this term is entangling gate. And in circuit language, this is written by this. So it consists of swap gates, CG gates, the power of alpha, and arbitrary single qubit gate. And it's known that flow XXZ model written like this have a representation in terms of dual unitary quantum circuit. And more interesting example is self-dual Ising model. It also have a representation of dual unitary quantum circuit. So they have a physically interesting model that is written by dual unitary quantum circuit. And as I said before, dual unitary quantum circuit arising from certain initial state. So I want to define here the initial state of dual unitary quantum circuit. So initial state is written by matrix product state. I expect that all of you are familiar with this tensor network. I explain briefly. So matrix product state is written by defined by matrix A that have this form, and the quantum state is defined by following form. And we want to define solvable initial state that have two conditions. First condition is something like unitarity of matrix A. So if we contract these indices I and alpha between A and A star, then this is equal to identity. So this is very similar to the condition of dual unitary gate. And the second condition is so-called injectivity of matrix product state, that which means that transfer matrix E has unique maximum eigenvalue. So we call MPS is solvable initial state if they satisfy two conditions. And the simplest example is chain of EPR pairs that have this form. So yeah, it is immediately seen that this satisfies these two conditions. So now I move on to my research topic, as I want to show how quantum computation power of one-dimensional unitary quantum circuit has been determined by using tensor network language. So now we assume that computational output is defined by local measurement outcome, which is equal to expectation value of local observables. And the problem setting is we fix the number of qubits n and determine computational power of dual unitary quantum circuits in time t. So we fix the number of qubits and we see computational power of this quantum circuit depending on the time or circuit depth t. And the problem is translated to the following problem, that to calculate local expectation value written in this tensor network. And first we want to focus on early time, that is that time is less than the system size n. And after removing outside of right cone, this expectation value is written like this. And after deforming the right hand side, this is equal to this form. And now by using the definition of dual-unitary gate, that is unitarity in space direction or lateral direction, we can remove the upper unitary and bottom unitary. So, and by repeating this procedure, we can eliminate these unitaries. And by using again about this top most right hand side top unitary and bottom unitary, we can eliminate like this form. And after deforming again and using unitarity to the bottom and upper unitaries, then we can remove this unitary gate. And at the end, the local expectation value is nothing but trace O. So it means that local expectation value or measurement outcome does not depend on specific choice of dual unitary gate. It means that this quantum computer cannot compute anything. So the problem is in P that is easy for classical computer, and even much weaker because it does not compute anything. And we can easily extend the result to a general solvable initial state, written like this form. And we want to compute this regime that have transfer matrix to the power of n. And from condition 1, we know that the Bell pair in virtual indices are eigenstate of this transfer matrix. And by using condition 2, this is a unique maximum eigenvector, so we can compute this transfer matrix as this form, where epsilon has exponentially small eigenvalues. So using this observation, we can calculate local observable again. So this is equal to here, and by using the definition of A and the unitary gate, we can eliminate these tensors again, and the local expectation values are equal to threshold. So that was early time, and let's turn to late time regime. So in late time regime, that is time is larger than the system size. Local expectation value is written like this form. And in contrast with the early time regime, this upper unitary gate and lower dual unitary gate are not connected by identity or are not contracted. So we cannot remove top and bottom unitaries like in early time regime. So the natural question is this quantum circuit is still classically simulable or not? And the answer is no, unless classical computers are as powerful as quantum computers. So the proof technique is so, following. So first, let us note that dual-unitary gate in general form can construct universal gate set if there were not swap gate. So dual-unitary gate include arbitrary single qubit gate and swap gate and CZ gate. And if there is no swap gate, it includes CZ gate and Adamar gate and T gate that constitute for universal gate set. So all we have to do is to remove swap gate from this gate set. And actually we can remove swap gate as followings. So let's write CZ gate as this this gate. And if we apply swap gate in almost all time, and if we apply CZ gate at single time point, then this dual-unitary quantum circuit is equivalent to this quantum circuit. Yeah, we can immediately show that you just track this qubit, and you found that this is equal to identity gate. So now we have shown that we can remove subgate from this unitary gate by using this redundant quantum circuit. And as I said before, CZ gate plus arbitrary 1 qubit unitary is can perform universal quantum computation. So in high depth, dual-unitary quantum circuit can perform universal quantum computation, which is outperforming classical computer. So I want to summarize the result. In early time, that is linear depth or linear time in number of qubit, the local expectation value are classically simulable because this is exact. This is equal to trace of local observables. On the contrast, in higher regime, dual-unitary quantum circuit can implement arbitrary quantum algorithm, which means that they can outperform classical computer unless classical computer is equivalent to quantum computer. So this is very interesting for quantum computation community because this computational complexity makes that transition in polynomial time. So in linear time, they are classically simulable, but in polynomial time, they can perform universal computation. And this is unlike this is contrast to conventional classically simulable quantum circuit, such as Clifford circuit and match gate, that they do not make a transition like this. So during the quantum circuit is first example where the computational power makes transition in polynomial time. And we have also considered sampling complexity of one-dimensional dual-unitary quantum circuit. The problem is to sample output of dual-unitary quantum circuit up to multiplicative error. And we will show that this problem is hard for classical computer. So the detail of problem is following. We first prepare a solvable initial state and apply dual-unitary gate in time t. And finally, we measure in this computational basis to all final quantum state. And we define measurement probability distribution from this measurement outcome. And we ask, is there a classical computer whose output satisfies this closeness? So we ask whether there exists classical computer that the output distribution is close to this dual-unitary quantum circuit. And in order to show the hardness of a classical computer, we use the well-known result that sampling from measurement output distribution of 2D cluster state is inefficient by classical computer under computational complexity assumption. 2D cluster state are defined by followings. So we first prepare plus state, which is +1 eigenvector of power x, and then we apply CG gate to all nearest neighbor plus state. And actually, we can generate 2D cluster state by 1D dual-unitary quantum circuit by using this form of dual-unitary quantum circuit. So we can show that this is so output state is equivalent to the cluster state. And because of this result, we can show that classical sampling from output distribution of 1D dual-unitary quantum circuit is hard problem. And next, we move on to the generalization of dual-unitary quantum circuit to higher dimension, specifically two-dimensional quantum systems. So the generalization to the quantum systems is also attracting for exactly solvable model of non-equilibrium systems, because in general, to the quantum systems, so exact solution to the quantum systems are harder and harder than one-dimensional systems. So it's also interesting for non-equilibrium physics. But anyway, I want to define 2D dual-unitary quantum circuit. The quantum circuit is defined by 4-period quantum circuit where we apply unitary gate to each qubit, like this form. So first, in even time, we apply unitary gate in lateral side, and in odd time, we apply unitary gate in vertical side. And we please note that we allow arbitrary 2-qubit gate, not only dual unitary gate, but arbitrary unitary gate at odd time. So this is a major difference between 2D and 1D setting. And the initial state, solvable initial state, is loss of initial state in 1D cases. So we arrange 1D solvable state. And we can also show that the local observable in early time can be calculated exactly. So the proof technique is very similar to 1D cases. So graphically, the local observable is written like this. This is a very rough figure, but in detail, the unitary gate forms this tensor network, and by using as with 1D cases, by using local definition of dual unitary gate, we can remove this dual unitary gate like this, and by using a unitarity of odd time, we can remove a unitary gate like this. So by repeating this procedure, we can calculate that this local expectation value is equal to trace one. So to summarize, the the computational power of 2D dual-unitary circuit where output is obtained by local measurement is like in early time, they are classically symmetrical. In late time, they can perform universal quantum computation. This proof is also similar to 1D case, so I skip this proof. But the interesting is we can obtain this computation complexity transition also in higher dimension. And I think it's non-trivial that this can be generalized to higher dimension. A classical symmetrical regime is generalized to higher dimension. And we also considered not only squared lattice, but also generalization to arbitrary or other lattices. And please note that in 2D dual unitary quantum circuit, unitary gate acting at odd time can be identity gate because unitary gate dual unitary gate doesn't include identity, but unitary gate, of course, include identity gate. So, for example, dual unitary gate defined on honeycomb lattice is also classically symmetrical in early time. This is because honeycomb lattice is equivalent to this rectangular lattice, and if we apply identity gate of square dual unitary gate on square lattice here, so this blue line is identity, then this quantum circuit is equivalent to this form. This is equivalent to honeycomb lattice. So we can say in general, dual unitary quantum circuit associated with lattice whose arbitrary vertical edges are removed are also classically symmetrical in early time regime. And we'll also consider sampling complexity into the case. And this problem is more simple than 1D cases because we can simply generate 2D cluster state by using 2D dual unitary quantum circuit. And interestingly, we can generate 2D state, 2D cluster state in time 4 or depth 4. And it's known that sampling problem of this depth 4 2D general quantum circuit is classically hard, which means that the hardness of sampling problem of 2D dual unitary quantum circuit is in this sense equivalent to sampling problem of general quantum circuit. Yeah, it means that the transitional point is very similar to general quantum circuit. So let me summarize my talk. So the conclusion is dual unitary quantum circuit, a new type of classical symmetrical quantum circuit where computational complexity highly depends on circuit depth. And it might be other relevant research on computational phase transition, which has attracted a growing interest recently. And I think that there are many future directions. For example, we don't have yet researched on computational power of the unitary quantum circuit with non-solvable initial state. And yeah, I think this modification would be interesting because in critical circuit or match gate, the modification of initial state makes change to computational power. So I imagine that computational power of the unitary quantum circuit with non-solvable initial state also changes with comparing to those with solvable initial states. And it's also natural to ask whether we can generalize our result to dual-unitary quantum circuit with open boundary conditions. And what's interesting for me is the other relationship between other exactly solvable models and quantum computation. This is end of my talk. Thank you for listening.
Okay, thank you, Suzuki-san. Thank you for interesting talk. So the time is up for discussion. Is there any questions or comment? Okay, Nishino-san, please.
In 3D, you have created the lattice by combining dual unitary gates. Is that the sufficient? I understand that that is the sufficient condition to construct 3D case, 3D lattice that can be treated in that manner. Okay, in this manner, you can construct cone, a solvable cone to discuss the same kind of construction. And is this, I understand that that's sufficient condition. So what's the necessary condition? I mean that, is there any other choice or wider choice of gates that can satisfy good conditions such as you have shown in 3D? Do you understand?
Yes, so are you asking what is the necessary condition that we can remove the unitary gate like this form?
So you can, for example, you can introduce a 6-leg tensor to construct.
Yes, sure.
So is this so as long as you create the that, okay, or you have shown 6-leg you have shown that that sort of 6-leg tensor can be created by the combination of 3 or 2. I don't understand, but anyway, combination of 4-leg gates. But is there a wider class of 6-leg gates that can 6-leg or 8-leg? I don't know. But
yeah, 6 gate. You mean this 6 gate? Yeah, I think that is very interesting question. And the answer is I don't know about necessary condition. Yeah, but yes. So I can imagine that. Yeah, I conjecture that all such solvable unitary gate is decomposed by this form, but it's conjecture. And actually I don't know the necessary condition, but I think that is interesting generalization. It will be interesting generalization. But
okay, I understand. You are honest man, so I don't know either. Okay, thank you for the
thank you for your question.
Okay, next is Okubo-san.
Thank you very much for your nice talk. I'd like to ask you about the relationship to the quantum dynamics with your dual unitary circuit. So I understood that your circuit corresponds to the quantum dynamics described by the even odd unitary pattern in the case for the 1D or 2D. And so we can consider some non-equilibrium system, some like special initial condition expressed by the solvable condition. So your phase transition may mean the dynamical phase transition in the quantum system. And so I'm interested in the meaning of solvable MPS or something like that. So does it mean the special, if we prepare the special interstate, the state remains, how to say, some non-thermalized state. And if we prepare another, how to say, general state, the state goes to the thermalized state. Is that correct? I'm not sure, but
the next thing is we can say first with solvable initial state, and in early time they equivalent to infinite temperature. correspond to that corresponds to local density matrix is equal to identity or yeah, maximum mixed state. So what I want to say is first in early time, because this is because local expectation value is trace O, which means that the local density matrix is equal to maximal mixed state, which means that in early time they is something like equivalent to infinite temperature. But the interesting is if we apply more and more gate, then this expectation value have some non-trivial value. It means that it's not necessarily equilibrated state. And so what I know is at early time, the local density matrix looks like infinite temperature state, but in later time, they behave some non-equilibrium state. But after long time, we can numerically show that it's equilibrate to some truly equilibration.
Okay, but I think the dynamical phase transition occurs at the t equal order of n. So the n
yes,
at n.
Yes.
And so if we consider thermodynamic limit, what happened? So the all at the all time the temperature is infinite. I see.
Yes.
And what happened if we change the initial state? So the this is a future plan. I don't know. So
yes. So if but it's not that if we take some non-solvable initial state, then the locus of the ball have a non-trivial value, so which is not equal to trace. So we cannot show the equilibration to infinite temperature state.
I see.
Yeah, but we can calculate something by using perturbation theory, so we can show analytically with close to solvable point, but yeah.
Okay, so at the beginning of this talk, you said that some Flock XXD model correspond to the this
yes.
W type. So okay.
Yes, and we can generalize this to the 2D case as well.
I see. Okay, very interesting. Thank you very much.
Thank you for your questions.
Okay, so Nishino-san again.
Related to Okubo-san's question, so in the longer time, the system becomes non-solvable, unsolvable. In the field of exactly solved models, there is a way to control boundary tensors so that it can be solvable with the presence of boundary. In that case, you have to choose the boundary condition so that the Yang-Baxter equation, some sort of Yang-Baxter equation is satisfied at the boundary. So is there any way to put a special tensor at the left side, left boundary and the right boundary of the system to keep the system always solvable regardless of the time?
So you mean by boundary, the boundary at initial state and boundary at the final?
No. That is a boundary condition, but there is another boundary at the right end and left end of the system. When
so you mean open boundary condition?
So now, if it is open boundary, if you put simply open boundary, this is not solvable. I understand that. But is there any way to put another special tensor to couple or couple another sort of tensor, special tensors at the boundary to and contract it and make the system solvable? Is it possible?
Yeah, I know there are some related research that exactly solvable model of boundary boundary operator, but
I have not considered.
Yeah,
Okay.
I have not considered.
Okay,
Yeah,
then
that's
I
interesting
just
for
put
them.
the comment that in the example,
Yeah,
exactly
thank you for your comment.
that there is a sort of system.
But I'd like to say that dual-unitary beyond Yang-Baxter equation in the sense that they include some quantum dynamics. They breaks integrability, some such as kicked Ising model. Sorry, I don't.
I understand. So this condition is wider than the Yang-Baxter equation. Is that correct?
Yes, I think so.
Okay. That's a good information. Thank you for that.
Yeah, thank you for your comment.